So we have a new state-of-the-art Chinese model. MiniCPM is a very interesting model because although it has only 8 billion parameters, it is able to achieve results similar and even better than GPT-4o on benchmarks connected to multimodal tasks such as audio processing, voice processing, video and image analysis. And in today's video, we're gonna talk about this model. We're gonna analyze the benchmarks and results of this model, tell what is this good for, what is this bad for, how can we use it. And then we're gonna take a closer look at the architecture of the model, where we're gonna talk how did they achieve such good results. What is the vision encoder, what is the audio encoder, and what is the LLM backbone and voice decoder. And we're also gonna talk about the training procedure that they use for. I think it is very good model to analyze because it is almost like a reference point, because in this model they don't have any breakthrough results or breakthrough research, but they did everything right. And in the end result, they achieved very good accuracy with very small size. So I got to say this model is very impressive because GPT-4o, we don't exactly know how many parameters it has, but it surely is way more than 8 billion. So in this open source model that you can run on device that doesn't even have a dedicated GPU, and they even state in the GitHub repository that they did some benchmarks on iPads with M4 processor, a model of such small size being able to achieve such good results, this is truly remarkable. So let's go to the benchmarks and firstly analyze the results reported by the authors. So as we can see, overall, the general sentiment is that the model is very good. It is able to achieve results better than previous state-of-the-art multimodal models, even closed like GPT-4o or Gemini. And overall, the results are very good. But we can see some areas, some benchmarks when the model's accuracy is lower than other models. So the first thing we need to do is to take a closer look at those benchmarks. For example, here at MMVet, the model is worse, right, than GPT-4o. So if we take a closer look at this benchmark, we might speculate why that is. So this is a specific benchmark that focuses on visual language model capabilities, but it is sort of a harder benchmark than standards, VLLM benchmark. So they compare themselves in this benchmark to other benchmarks, and as you can see, in most of the benchmarks, the questions are rather straightforward, like is the boy happy? So it is something that can be easily inferred from the image. Or for example, right here, what is the largest denomination on the table? No deep thinking, just straightforward answer based on, analyzing the image. But on this benchmark, the situation is slightly different. So they have harder questions. So not only do they ask what is written on the blackboard, but is the answer right? So the LLM has not only to do OCR, analyze the image, but also do some very basic but still reasoning. And on the other examples, we can also see this. So for example, there is a question, where is this photo taken? So it is not a question of what sport are they playing? The answer is soccer. But the question is, where was the photo taken? So the model has to have some word knowledge. It has to know that there was a championship and it was done in Qatar. So it tests beyond simple image recognition capabilities. And in the next example, we also have analyzing a meme. So the model has to have the notion of humor. So it is a slightly harder benchmark that checks word knowledge, checks reasoning, etc. And another example of a benchmark where this model has slightly lower results is this one. And in this one, it is also a collection of college exams from various disciplines, like art and design, business science. So here also we have harder questions that are connected, to some quizzes, and it is not enough for the model to do OCR and to recognize what is on the image, but it also has to solve some problem, right? So this is a problem for a college student. So we can expect a certain level of reasoning, of also knowledge and both reasoning. So solving mathematical problems, analyzing, comics about connected to some political events and stuff like that. So also harder benchmark. And the last one that we're gonna take a look at is called Blink, and this is also a benchmark designed specifically to compose of questions and images that are very easy to human, like done within a blink. But for LLMs, they are harder. So this benchmark focuses specifically on challenges harder for LLMs, and we also have some examples of IQ tests, some examples of reasoning, and some deeper word knowledge. So we see the trend, right? On harder benchmarks, benchmark connected to reasoning, word knowledge, etc., this model doesn't achieve results quite good as, for example, GPT-4o. But then again, from my perspective, it is not surprising, right? Because we have a model that has 8 billion parameters, and okay, there was a huge progress recently with 8 billion parameter models, but still those models are very small by modern standards. So they are not able to comprehend those harder questions. And by design, by principle, you can't store enough word knowledge in 8 billion parameters to answer all of those questions accurately. It is a lot easier with enough training data to store those information in the larger models, because you have to have a space to pour the knowledge into within the LLM. But my takeaway is that do we really need reasoning models for everything? Because some tasks are easy, right? They require OCR, image classification, some simple image analysis. And with those tasks, such model is very good and it actually excels, right? Is better than the closed source alternatives. So we don't need one generalist model, and this model is not a generalist. It is for very specific capabilities connected with image and audio processing, and within those areas, the model actually excels. So it is very good model for those kind of questions. So if we were to sum up what this model is good for and what it isn't, what should we and shouldn't we use it for, definitely OCR. If you need to do any kind of OCR, especially on device with small models, you can definitely use this one. ASR, so automatic speech recognition, also very good if you need to transcribe audio. I don't know how it compares to models dedicated ASR models like Whisper, for example, but definitely if you need, but Whisper only does the transcription, right? And this model does some basic reasoning. So if you need to clean up the text or do some kind of basic analysis, definitely better. Math, we have some good results on math benchmarks. For example, Math Vista, it is quite good. But then again, on other benchmarks that also compose of harder math questions, we see that the model is not the best. So maybe simple math, right? And also, of course, the primary goal of analyzing images, so visual question answering. If we need to answer some questions that are answers to are present on the image and they don't require deep reasoning or deep word knowledge, definitely the model is good for this. And of course, what the model isn't good for is, as we already said, word knowledge, reasoning. But then again, we don't really need every model to have all the facts in the world. I think we are moving in the motion of specialized models that are good for specific range of tasks, and this model is that. So we can see that the results are very impressive. This is 8 billion models that you can run on device, and it actually beats models like GPT-4o. So the question arises, how did they do this? So how did they achieve so good results? And we actually have a technical report. It is not very detailed. It has a Notion post, but if we were to translate it to pages, it has about 10 pages or so. So, there are much more in-depth technical reports. But we do know a bunch of things. We know the architecture of the vision encoder, audio encoder, LLM, etc. We don't know everything about the training dataset. So how does the model work? So the model is, its gimmick is that it's multimodal, right? So it can accept input in form of audio, in form of images, in form of video, which is just a set of images. And also it is able to generate audio. So it can answer us not only in a text way, but also it can speak to us. And we can actually have a natural conversation like with GPT-4o voice mode, when you ask the model something and it responds back to you, but not just by typing text on the screen, but actually responding with voice. And it is able to do this both in Chinese and English. Unfortunately, it is not multilingual like models like 4o, but then again, we can't expect too much from an 8 billion parameter model. So this is the general architecture, right? We accept the inputs from different modalities, analyze them, process them within the LLM, and then we are also able to generate two modalities, either text or audio. And we can look at the individual components, because the way we do this in general is we have a dedicated encoder that transforms the raw format of data to a format vector representation that can be understood by machine learning models. So we of course have dedicated encoder for audio, dedicated encoder for images, and then also if we want to then decode it, so for example generate speech, we also have a dedicated speech decoder. So those are like the add-ons to the core LLM. And the way they did this, they chose state-of-the-art small components from all of the areas. So we have very good image encoder, very good audio encoder, very good small LLM, and very good voice decoder. So let's move on to the voice encoder. So the thing is, with this model, it is able to analyze images at very high resolutions. This is like the main advantage. And the way they did it, they introduced some clever mechanism that we're gonna talk in a bit. But firstly, let's look at the what kind of model they used. So they used SIGLIP model, which is a version of a CLIP model, a model trained in a similar way as CLIP, and this is also a vision transformer. So what does it mean? A CLIP model was actually developed by OpenAI, and it is a specific type of model that uses contrastive learning to learn to analyze images and text. And the way they train the model is they generate a set of images and labels, and then the image encoder and the text encoder, they both encode text and image, and the way is to maximize the similarity between the image and its actual caption and minimize the similarity between all other captions. So you can see this here. We have a set of images encoded, we have a set of text encoded, and we want to maximize this similarity on the diagonal when we have corresponding image and labels, and we want to minimize all the other distances. And the way with contrastive learning is that it is very effective in learning representations, because the goal is not to create a captioning model in a sense, but a model that is able to encode the images very well. So put similar images close together in this vector space and the similar images far apart in this vector space. And contrastive learning, through the training, you actually learn to pull together the similar images, the embeddings of the similar images, and push apart embeddings of dissimilar images. So we're not showing the model like this is the description of the image, but we're showing the model this description and this image is similar. You should treat it as the same. And with other images and other descriptions, we tell the model those are not the same things. You should treat them differently. And through the iterative process, we are able to create very good representations by enforcing model to pull together similar representations, similar images, and push apart different images. So this is the CLIP model, and it is basis of the SIGLIP model that they use. And this is also vision transformer model. So the way the vision transformer works is it uses a transformer architecture similar as in LLMs, but to analyze images. And it works by separating the images into patches. They are, for example, 16 by 16 pixel squares. And then once we have those patches, we can treat them as a sequence. And we, of course, do some positional encoding to have the notion of the sequence. But then we use regular transformer to an attention mechanism to sort of create contextual embeddings of those patches. So we have static embeddings at the beginning, and transformer, through its attention mechanism, the different patches, their embeddings attend to each other, right? So we have a representation of this specific fragment of the image, but in the context of the whole image. And vision transformers are very effective, even better than convolutional neural networks, but if they have enough data and enough parameters. So for small applications and limited data scenarios, CNNs are usually still better, but if we have a large volume of data we can train on and a large enough model, vision transformers achieve state-of-the-art results. And the last component of the vision encoder is called dynamic tiling, because I told you at the beginning the biggest advantage of this encoder is that it's able to encode large images. And how did they achieve that? So in standard vision transformer, we have a fixed size patches. So we have those squares like 16 by 16 pixel, right? And if we have a larger image, then we have a larger amount of patches because the size of the patch is constant. So if the image is larger, then also we have more patches. But in dynamic tiling, the number of patches is constant. So if we have a smaller image, then we have lower resolution of the patches. And if we have a larger image, we have higher resolution of the patches. So we have variable patch size, but fixed number of output token. And in this architecture, they used 640 tokens for the entire image, no matter what the size. So if we have a higher resolution, lower resolution, if it's a square, if it's horizontal, vertical, doesn't really matter. We always get 640 tokens per image. And by doing this, we can limit the number of the tokens we need to represent the image. So actually, this model uses 74% fewer tokens than the most of the models would produce. This is straight from the technical papers. And we can see in comparison to other models, we have a higher pixel density. So this means we can encode more pixels in one patch, in one token. Of course, this is a trade-off, right? Because we can then lose some information because we have lower amount of pixels per token. But on the other hand, we are able to do this super fast because we use the fixed number of token. The processing time is constant, really, because it doesn't matter if the image is large or small. We can analyze both of those images very fast. So, of course, this is a model designed to run on device, right? So it's understandable that they chose architecture that is able to achieve that. And through the benchmark, we can see we have actually very little degradation in results. So key takeaway, designed for efficiency and high resolution images. And it can actually take up to 1.8 million pixels, right? And the highest aspect ratio for this is 1300 by 1300 pixels, but it can be arbitrary ratio, right? So it has to sum up to at most 1.8 million pixels, but it can be vertical, horizontal, doesn't really matter. So again, as I said, a very good encoder, state-of-the-art method for creating embeddings using clip architecture, state-of-the-art, backbone using vision transformer, and some tweaks to enhance efficiency. Then we have audio encoder, right? So maybe just to sum up, at the end of this process, so going through the image encoder, we have those embeddings, right? Those vectors representing the image that are fed to LLM, and then the LLM analyzes this to generally in the same way as it would text. So how do we represent audio? In audio, they used Whisper Medium 300 million parameter model as the speech encoder, so a model that represents the speech as a vector. And Whisper is again was designed by OpenAI, and it was used for speech recognition. But here they do it's slightly different, because it's not like we firstly have audio and then the model does transcription, and then we have text and then we feed the text to the LLM. We feed the embeddings to the LLM. So there is no ASR during this process, speech recognition. We just encode the speech and then feed it to the LLM. And it is, of course, we have advantage of encoding some features that wouldn't be present in the audio transcription, like emotion, like certain sounds that doesn't produce textual results. So they used model pre-trained in to do transcription, but they use it as feature encoder. So the way Whisper works, maybe we won't go into that such a depth in this model, but it takes a MEL spectrogram of the speech, and this is a special kind of spectrogram that is designed to encode human speech in most representative way. Then it has some convolutions, and then we also have transformer encoder. So we also have self-attention mechanism. So similar way that we have in the image encoder, here those different parts of the speech, of the audio, attend to each other and sort of create contextual representations that are then in Whisper used to produce the transcription. But here we don't have this part, right? So in this kind of model, in our model we got rid of that's slightly large. Maybe let me check this one. Okay, let's get rid of that. And here they don't do decoding, right? So they don't produce the text, rather they feed it straight to the LLM. So what else can we say about the speech encoders? Takes a waveform, writes a spectrogram, does an intermediate step, and then produces the audio token. And here we have these audio tokens that are specific to this model. So similar as we have text token, here we have audio token. No uses hidden representation, no ASR is performed. And also here they designed it for efficiency. So standard Whisper produces 50 tokens for 1 second of audio. We're talking about these audio tokens, right? Virtual tokens, not words. And inspired, as they say, by other LLMs such as Lava, they reduced the number of tokens per second to 25, so by half. And it's as was shown in the Lava paper, it doesn't degrade the output. So we can optimize it, we can decrease the number of tokens, and we have no or little degradation in the audio. So again, same pattern we saw in the image encoder. State-of-the-art audio encoder, but some tweaks to maximize efficiency. And then, of course, once we encode both speech and images, we have to have the main brain of the operation. So the LLM to analyze the data, to reason, to put it in context. And here they use Qwen 2.5 as the backbone. And Qwen is also one of the state-of-the-art models for its size. They use 7 billion parameter Qwen. It is also multimodal, so it was also able to understand those components from Siglip and from Whisper encoders. It serves in this model as a reasoning engine. So once it accepts the encoded representation, it is able to reason over them and answer questions and produce output. And it is also responsible for the text generation. So it either generates text in a straightforward way, or it generates special tokens that are later fed to the text-to-speech engine. So the LLM actually decides if it wants to respond in text or does it want to respond in audio. And if it decides to respond in audio, it gives instructions how to generate this audio to the another component that we're gonna talk in a bit. And we also have some notes about training that we're also gonna talk in the last part. So the model learns cross-modal alignment, right? So it is able to mix together different types of inputs. So for example, question and then image, or voice and then text. So we don't have to, respond only in ask the model only in text or only in voice. We can mix those modalities. And another reason I suspect they chose Qwen 2.5 was because it's already designed to handle multimodal data well. So it was able to, they were able to more easily fine-tune the model. And when we talk about Qwen, also one interesting thing about the model is rope positional encoding. And here we have a tutorial by Hugging Face. I'm gonna leave the link in the description because it's a very good tutorial. So if you're interested in how it works in depth, definitely check this out. It compares different types of encoding. We're not gonna go into super deep in this area in this video, but if you're interested, definitely check this out. But just quick overview how the embedding works. So we have the standard word vectors, right? And we can represent them as vectors, so as an arrow with direction and length. And the way rope works, it adds the sense of time, let's say, to the input, because standard transformer processes everything at once. So it has no notion of what word was first, what word was last, what is the order of the words. And there are many ways to give the model the sense of notion of time, of order of words. Standard is, for example, using functions such as sine and cosines and functions to give the notion of time. But here they do something different. So they use rotations. So the magnitude of the vector is the same, but it is slightly rotated in different directions as we move through time. So we give the sense of order and the sense of time by rotating the vectors, word embeddings, differently as we move through the sequence. And rope encoding is like currently considered state-of-the-art positional encoding. So again, nothing new in this area, but using state-of-the-art components. And lastly, we have this voice decoder, right? So we said that LLM generates special kind of voice tokens as an instructions to how to respond in voice. And voice decoder uses those tokens to produce the audio. And it is based on chat text-to-speech, which is, again, small model, but considered state-of-the-art in its size category. And it is trained to produce natural human-like speech in multiple voices. And the way it works, it also accepts prompts called system audio prompt, as they call it, to guide the generation process in characteristics of the voice. So it should be male voice, female voice, older, younger, happy, sad, stuff like that. So we actually don't have a diagram for this one, but I created a simple diagram showing how it works. So we firstly have the system prompt, system audio prompt, right? That we are able to create to steer the model. And then we have those special voice tokens that are outputted from the LLM, from Qwen. Then we have this model, and it also generates spectrogram that is then converted to audio. So we are able to generate representation of the audio, intermediate representation, and then the audio itself. And what is interesting about this model, it is also, and it enables the MiniCPM model to be end-to-end conversational agent, right? So as we said at the beginning, we can ask the questions with our voice, and the model can respond also in a voice way. So we have this like assistant, and yeah, keep in mind those system prompts, because it's also super interesting, and I think it's quite cool that they are able to do this, and you can steer the model. So for example, if I'm doing like personal assistant or voice bots on phone calls and stuff like that, you can actually prompt the model to have calm, assuring voice, or you can prompt the model to be angry if you want to, or you can prompt the model to have specific persona, specific voice persona. That is also super cool in these applications. To be honest, I haven't checked how well it encodes those kind of features. They have them on their website where they show male and female voice, and it works quite well. But I'm not sure how, and I don't think have any benchmarks showing how good it represents those more specific instructions of about the generated voice. But it should be good. So what is our takeaway? I told you this model is a very good case study. If we were to have a class about how to create multimodal LLMs, this is like the golden standard, because they took state-of-the-art vision encoder, state-of-the-art audio encoder, of course for these specific sizes, right? State-of-the-art LLM, one of the state-of-the-art LLMs for its size, and then also very good voice decoder, and they just stuck them together. So took the best of each category, but of course stacking them together is not enough. We have to actually train those components to work together. So how was the training done? So there were two phases. So firstly, or three phases. In the first phase, that wasn't done specifically by the authors of this model, but they took components that were already pre-trained. So as I told you, Siglip was trained using the clip method on contrastive learning. Whisper was trained for transcription ASR. Qwen was trained for their own language modeling, and ChatTTS was trained for generating audio. But they didn't start from scratch. Like all of those components were already working and doing their thing. The thing that they did is they put them together and then created a joint fine-tuning. And in the joint fine-tuning, the components or the whole model that is a result of those components learned to work together. So they used variety end-to-end instructions, multimodal instructions. End-to-end meaning, the input could be in audio, the output could be in text, the input could be in text, the output could be in audio, mix of those, end-to-end modalities. And then they trained the whole thing together. And notably, all the components were updated together. So the way you sometimes do it is, for example, you train one specific part. So you say, okay, now it's time to focus on image reasoning, and you fine-tune image encoder, and the LLM is frozen. Or in another way, you keep the image encoder frozen, and the LLM is the only one learning, right? But here they did no freezing of the different parts. All of them will learning together simultaneously to work together to solve the problems. Yeah, and we already told they used both system prompt for text-based task and this audio system prompt for voice. And the training involved mix of modalities. So, for example, a prompt saying, here is the image, and then those encoded tokens of the image, then the user question, and then the model was trained to generate the response. And so, again, nothing out of order, I would say, on the training part. We don't exactly know what dataset they used. They have, we can guess and they give some details, but we don't have like the fully dataset open source. But we can expect that it was, standard datasets connected to multimodal reasoning. There are a few of open source ones. So yeah, keep in mind that all of those components were trained together. No component was frozen, and the input was mix of modalities. So they were not separated, and this was like the main goal of the model, right? For those components to work together to solve complex multimodal tasks. And the model also supports chain of thought prompting, right? So those reasoning that we currently have, which is like, important because has recent papers like models like DeepSeek or O1, O3 show reasoning is quite effective, right? So we can extend the time of inference, let the model talk to itself, and it is able to achieve better results for it. So it is good that this kind of model supports this type of prompting. And lastly, we have alignment and refinement, because this is like 3 steps to achieving LLM. First, you do the pre-training, for example, causal language modeling, just predicting the next word in the sequence. Then second stage is instruction tuning, teaching the model to solve user queries. And then the third part is alignment, so fine-tuning how the model behaves. Technically, multiple answers can be correct, but one is structured better. One is more to user liking, or some answers could be dangerous or biased, and we don't want that. So this alignment here takes care of that. And they used a method called RLAIF, which is like opposed to standard reinforcement learning from human feedback. That was, for example, done in the original ChatGPT. They here have reinforcement learning with AI feedback. So the model generates several responses for the same query. We can do this by, changing parameters like temperature. So it is not deterministic, it is rather, it generates multiple answers to the same question. And then we use external LLM like GPT-4 or some other better LLM to judge the responses. So the AI then rates the responses, and of course it has some prompts, right? So we give the guidelines and the way it should judge the responses, but we do this with AI rather than humans. And it has several advantages because firstly, we can exactly tell the model what thing we like, what we don't like. And with humans, it is always personal preference. So we can steer that. On the other hand, it is cheaper, right? Because passing the query through LLM is a lot cheaper than giving this task to humans. And it is like the general trend we see is those synthetic data, but not synthetic generated out of thin air, but grounded in some text, or like here using LLM to just judge the responses. Because in general, LLMs are much better at judging if a response is correct than generating the response without hallucinations, for example. So even though some models can detect hallucination in response, they still generate hallucination. So using LLM as a judge here is very efficient. But again, this kind of training is nothing like revolutionary, I would say. So yeah, I think we covered everything about how the model works. So to sum up, as I told you, very good, small, very impressive model for voice and for image analysis. Definitely check this out if you want to. They have both an online demo where you can chat with the model or even talk with it, and they also have very good instruction on how to run the model using Llama CPP or VLLM or other popular tools to run those models locally. It is super easy. They have this process well documented, and if you need any kind of multimodal processing, definitely check it out. So that's all from me. If you like the video, don't forget to like and to subscribe to our channel, and I will see you when the new interesting LLM comes out.